Welcome back. Today we'll begin the final chapter of this course that deals with fluxes under simultaneous multiple driving forces. Okay. So far, we have seen the flux associated with its primary driving force. Now we are going to throw it open, and thereby, this is whatever we are going to see in this chapter is closer to reality. Typically, you have multiple driving forces at the same time. We have already seen that the maximum flux may not arise from, or most likely will not arise from, the primary driving force. It's just that it is firstly associated with the flux. That's all. Okay. Now we're going to put everything together. And I think this approach of looking at that separately, understanding that clearly, and then bringing things together would help you in obtaining a certain flow, and thereby that will improve your understanding. Okay. Let us start looking at this in this chapter, just an introduction today, and then we can take things forward as we move along in the course. Thus far, if you look at the flux of quantity, the primary driving force, a constitutive equation. When we were looking at mass, the primary driving force was the concentration gradient, and the constitutive equation was the fixed first law, Ji star equals minus di dci dx. I'm just going to write one dimension so that you can better appreciate, or it's more intuitive. Okay. So mass is, of course, was conserved. Momentum was also conserved. The primary driving force for momentum flux was velocity gradient, and Newton's law was a constitutive equation, tau yx equals minus mu dvx dy. There's also a direction of motion and a direction of action, and so on and so forth. There could be combinations in 3 dimensions. Then we looked at thermal energy, which of course is not conserved. Starting with the energy balance equation that gave us left hand side equals right hand side, we nicely pulled out the thermal energy. Or if you look at the book, it will be clear how the thermal energy was pulled out. The primary driving force was the temperature gradient, and a constitutive equation was Fourier's law, Qx equals minus k dt dx. And then, before this chapter, we looked at charge, which is of course a conserved quantity. The primary driving force was electrical potential gradient, and a constitutive equation was the Ohm's law, I dash equals minus ke dou v dou x. Okay. Potential gradient is the primary driving force associated with charge flux, and conductivity is the constant of proportionality. In normal practice, many driving forces simultaneously act in a system, the biosystem that we are looking at. Therefore, there could be simultaneous fluxes of mass, energy, momentum, charge, and so on and so forth. Further, there could be significant interplay between the different driving forces for the same flux, or different driving forces and different fluxes, okay, whatever it is. For example, mass flux could predominantly result from a velocity gradient. We all know what convection is, right? Related to motion, there could be a huge mass flux because of the motion of the liquid itself, which is many orders of magnitude higher than the flux that is caused by the concentration gradient. Okay. So far we have carefully avoided this situation when we looked at mass flux. Okay. We had seen situations where there was no motion of the fluid, where there was no convection, no bulk flow. Therefore, we could put those Vx, Vy, Vz equals 0 and so on, or Vr, V theta, Vz equals 0 and so on and so forth. That's what we have seen so far. Now we are going to remove all those constraints. Or momentum and mass fluxes could result from a temperature gradient, which is nothing but free convection. We will consider the situations where multiple forces simultaneously act, or multiple driving forces simultaneously act, and multiple fluxes simultaneously occur. For example, mass arising from multiple driving forces could be, okay, that expression comes later. Mass flux could arise from multiple driving forces, as I just mentioned. Of course, the concentration gradient one would always exist. Then there could be convection, there could be a temperature gradient, there could even be a charge gradient. Okay, we'll see that, which causes mass flux. The driving force for the mass flux could be one of the combinations, one or combinations of many. You could have a concentration gradient causing a mass flux, as I just mentioned. You could have an electrical voltage gradient, which is causing a mass flux. Recall electrophoresis. Their electrical voltage gradient, potential gradient, caused a mass flux. A pressure gradient, which results in convection bulk flow, that causes mass flux significantly. A temperature gradient, as in the case of free convection, could. Okay. And we are going to represent these aspects, concentration aspects by a C, electrical voltage aspects by a E, electrical aspects by a E, pressure aspects by a P, and temperature aspects by a T. If we do this, when many forces simultaneously act, the total flux of component I, because many different driving forces are causing mass flux here. So the total flux or total mass flux of the component I is nothing but a vectorial sum of the individual fluxes. Remember that flux is a vector, okay, it has direction. Therefore, it's a vectorial sum of the individual fluxes resulting from each driving force. That's quite straightforward. Therefore, the net molar flux in this case, Ji star, equals the molar flux due to the concentration gradient, the molar flux due to the electrical potential gradient, the molar flux due to the pressure gradient plus the molar flux due to the temperature gradient. Of course, all these are vector sums. This is equation 6-1. For example, when DNA and proteins are separated on electrophoresis gels, you certainly have a concentration gradient. Okay, there is a difference in concentration of protein from one end to the other. And of course, there is an electrical potential gradient. Okay. In fact, the flux due to electrical potential gradient would be much larger than the flux due to concentration gradient in electrophoresis. Now, let us look at the approaches that we are going to take in this study of multiple driving forces, multiple fluxes. When multiple forces are simultaneously operational, multiple driving forces are simultaneously operational, the approach is to simultaneously solve the relevant conservation equations. We have a conservation equation for mass, continuity equation. We have a conservation equation for momentum, the equation of motion, conservation equation of energy, right, the thermal energy equation, just recast around, and of course the electrical continuity equation. All these could be solved simultaneously to get the solution. Okay. Just to list: equation of continuity for mass conservation, equation of motion for momentum conservation, the thermal energy equations. Note that thermal energy is not conserved, but we got this from energy conservation, and the charge conservation equation along with the Maxwell's equations, of course, because the development has happened in terms of the Maxwell's equations. And in many situations, the formulations and solutions, of course, could get highly complicated. You have a set of coupled partial differential equations of highly complex nature, each one. It's going to get very messy mathematically. In principle, yeah, it is possible to express this, but the mathematical effort is going to be so significant that you might want to take a second look at that approach. Thus, an alternative approach is to use a less rigorous but useful approach that involves something called transfer coefficients. Transfer coefficients are nothing but equivalent of conductances, whatever mass conductance, momentum conductance, and so on and so forth. Okay. For example, mass flux is represented as a product of a certain mass transfer coefficient, okay, times the change in concentration. This is no longer a gradient, this is just a change. Of course, the change occurs over a distance, so that gradient aspect is inherent, but we are not going to take that into account in our formulation. We are just going to say that the mass flux equals a certain mass transfer coefficient times the difference in concentration. That's it. So this is the less rigorous approach. You cannot rely on molecular aspects as you could so completely when you did diffusion. Okay, when we did diffusion, you could do that, but here you cannot do that. And heat flux is expressed as a heat transfer coefficient times the difference in temperature. Okay, so this is a difference, not a gradient. The transfer coefficient approach is useful for analysis, design, and operation, and in some cases provides good insights too. In the remainder of the course, I think which will happen starting from the next class, we will discuss some examples of the above two broad approaches. Okay. To repeat, the first approach was to simultaneously solve the complex partial differential equations that correspond to all these conservation equations: equation of continuity, equation of motion, thermal energy equation, the charge conservation equation, this resulting from the energy conservation equation, and the charge conservation equation. So you write all those equations, you solve them, in principle you must get the solution. Okay. But the mathematical complexity is going to be so great, and therefore we look at a different approach. That is the transfer coefficient approach, which is highly useful. Okay. A lot of examples with respect to this, which we directly use in the bioreactor context, in various analysis contexts, which I'll show you. Okay. So here the formulation is something like this. The flux is given as a product of a transfer coefficient times the change in a certain quantity, which is equivalent to the driving force quantity. It's no longer a gradient, but just a change. For example, mass flux is a mass transfer coefficient times the change in concentration. Heat flux is a heat transfer coefficient times the change in temperature, and so on and so forth. I think that's all I have for this class. Yeah, it's a good time to stop. This is the introduction class, some sort of an orientation as to how we are going to approach this complex realistic situation. Okay. When we meet next, we will start with two driving forces causing a mass flux. See you then.